Good afternoon all. Myself Dilip Kumar SM. I am going to present one of my paper titled EASM Energy Aware Sync Mobility Algorithm to Prolong Network Lifetime in WSN. The outline of that presentation is like this. The earlier speaker who has worked on sensor networks gave a brief overview of the applications, its typical network, how it works, etc. So here I'll start with the issue of energy conservation, energy depletion, these kind of issues. The main reason for energy depletion is that since sensor network works with many to one traffic approach, the nodes near the sink always gets drained due to large processing of packets. And the second reason is that it is basically they are lightweight nodes, and the third reason is that they process data redundantly. The data itself they are redundant. When the data moves towards the sink, more data which are redundant will be processed by the nodes. So energy depletion happens. And another reason is that the formation of energy holes. If any nodes dies and if it is not forwarding the data or any other regard of that matter, the nodes will not function properly and the forwarding of data will not happen. So this this leads to formation of energy holes. So these are the typical reasons for energy depletions. So with this motivation, so we have selected few papers to limit. We have selected some 5 papers out of this. The first paper talks about distributed algorithm for reconstruction of a tree if a node fails during the aggregation process. And the second paper concentrates on creating a shortest path when the node when the sync node moves from one place to another place. It is more focused on reconstructing the shortest path tree. The third algorithm focuses on like creating a routing protocol for delivering the message. And the fourth paper is our own paper. So this paper divides the entire network into equal sized zones so that you can distribute the network over the network, and so you can monitor all the activities of the network. So in the fifth paper, we have this is also our own paper. Focus on finding the optimal multipath from source to destination. With this limiting to these 5 works, and we came out with a simple problem of gathering data from all the nodes in the sensor network, and once you collect the data, you aggregate them, so and then forward to the sink efficiently in a wireless sensor network. So this is the problem. For this problem, the objectives are to improve the lifetime of the network and to increase the amount of data gathering, as well as increase the data aggregation efficiency. So with this problem and the given set of objectives, we proposed a network model of this kind. So we had a undirected network graph represented by G is equal to vertices and edges, and then the entire network was divided into it was considered like a grid, and like this as it was shown in this figure, where you can see entire network is like a grid, and we are divided into equally sized zones so that the number of nodes are clustered physically. And for simplicity, we have assumed a sink placed in the center so that it can collect data from all the nodes of the network. So with this, there are some typical applications where there will be static nodes, sensor nodes, and the sink itself we can move from one place to another place. So here it's a very simple assumption of a network where there are 9 equally sized zones. Suppose if the number of nodes are more than this of this area, the number of subgrids will be more, the number of zones will be more, and this has the possibility of moving from one place here from one place to another place during some conditions. So always the sink moves towards the potential subgrid. The potential in the sense that where the subgrid which has more energy. So with this, the methodology is that first the sink will understand who are the first one-off neighbors using the hello message. So with this hello message, the neighbor sends what is their residual energy to the sink. So the sink now calculates the average residual energy of all its one-off neighbors, and also in a similar fashion, it will also calculate the average residual energy of all nodes in the subgrid, so that each subgrid will have a residual energy of its of the subgrid. So based on these two parameters, the one-off neighbors and the residual energy of the subgrid, the sink will categorize the energy level into 4 levels, namely one is the adequate level, operation level, warning level, and danger level. So these are being normalized from 0 to 100% like this. Similarly, the average residual energy of all the subgrids is RE, SG subscript RRG for I is equal to 1 to 8. That is, if this is the thing, and the neighboring subgrids are there are 8 in number. So hence, each of the grid will calculate its residual energy. So once the residual energy is calculated by each of the subgrid, the maximum of this is computed here. This is called the energy status. The energy status of the maximum of 8 subgrids will be taken, and then so once it has then based on this energy status, the sink will decide whether to move to some position or not. So this energy status will determine whether the sink has to move or not. So the overall idea is that let the sink move from one place to another place only if the current subgrid don't have an adequate or operational energy level. Suppose if they don't have an adequate or operational energy level, it moves to any one of the 8 regions. So with this sink movement, if the energy status of the subgrid is at the adequate or operational level, then there will be no change in the current location of the sink. Otherwise, if not, the sink decides to relocate its to a new potential subgrid that has the maximum residual energy. So it has 8 options based on the maximum of any 8 subgrids. It decides whether to move or not. Then with this simple idea, we have there are some simulated results. So this is using the MATLAB toolkit. So the overall idea is to make a statistical analysis of how the number of nodes, how about the number of nodes, how the number of what is the lifetime of the nodes with so many number of nodes, or what is the number of sink movements like this. So in earlier works, there are like if a sink is mobile, it moves throughout the network. Here in this case, it is not necessary to move from one place to another place by the sink, because the thing is that if it starts moving from one place to another place randomly or continuously, each time the routing tree or the trees has to be reconstructed. So constructing a routing tree is not feasible because it has a lot of complexities and a lot of computations has to happen, and reordering and restructuring should happen. So here the sink will move only when the energy status is not adequate or in the operational level. So with this results, the y-axis is normalized from 0 to 200. With the number of nodes, in the y-axis, and with the number of rounds in this one. The number of nodes which has depleted, the average lifetime has increased in this work compared to the previous 2 works which has been considered in the literature. The second results talks about the energy in joules in the y-axis and the number of rounds where the algorithm is run. So comparison of residual energy, where this EASM, our algorithm, has produced slight better results than the static sink approach. The third results, the total amount of data gathered, which has been normalized from 300 to 400 because a lot of data has been collected only during this this one. The sink movement, as the time proceeds, the number of the amount of data gathered by the sink should also increase, because we need to gather data from all the regions of the network by the sink. We conclude this work by stating that we have proposed an energy aware sync mobility routing algorithm to prolong the network lifetime, collect and aggregate data efficiently in a wireless sensor network. So, since it is we have used BFS algorithm which constructs a minimum spanning tree during route construction, because when a sync moves from one subgrid to another subgrid, it has to reconstruct the spanning tree, and of course, the time complexity is big O of V plus E, the vertices and the edges. So, it is observed that the network lifetime, the residual energy and the amount of data collected as improvements over the other two algorithms. And to again conclude, sync mobility is always application specific. If the application demands sync mobility, then it can be, these kind of algorithms can be applied. Future work, and of course this basic idea of moving from one subgrid to another subgrid is a very simple approach, but in the future, in the future work, we have already extended this work of predicting the average residual energy of all the subgrids in the network. Suppose if one sync has the option of moving has the option of moving to another subgrid which has 8 options. If we consider more number of subgrids network, as the network increases or the size of the network increases, we need to predict, if you go in this direction, what could be the residual energy, or if you go in this direction, what could be the energy. Based on this, if you could predict the subgrid of n steps, then it could be possible, so that the sync will make a proper decision in using the residual energy of the node. So that if you do this, the entire you can balance the amount of energy distributed over the network. So suppose if that is done, ultimately the network lifetime will definitely increase. So this is the overall objective of this work. So predicting the residual energy of the entire network can be done using has been done using a machine intelligence algorithm. Okay. So addressing delay in packet delivery and packet drops during reconstruction is also important, which has to be considered, and we are considered, and shortly we are submitting that to a journal paper. So these are the references, just 5 references which I have stated in the literature survey, and the last 2 is our paperwork, and the 5th paper is published in WPC Springer in 2018. Thank you. I would like